So in this video I want to prove the counting theorem for gappy sets. So the theorem is like this. So if we look at GNK, so GNK is by definition a set of gappy sets. So this is going to be the number of gappy sets of size n, of size k, in the set 1 up to n. Okay, so we're looking at subsets of 1 up to n of size k, and they're supposed to be gappy. In other words, there's no two adjacent elements. Okay, so the claim is that this is n minus k plus 1, choose k. Yeah, this is only valid in the case where this is a sort of a normal binomial coefficient with n minus k plus 1 greater than or equal to k, which is the same as saying that n is at least 2k minus 1. Okay. Okay, and so we'll we're going to illustrate this for the case n is 7 and k is 3. So the claim in that case is that, mod G73, so in this case n minus k plus 1 is going to be 5, so this is going to be 5 choose 3, and 5 choose 3, just work it out, that's 10. So how does the proof of this result go? So we're going to say, well, what's the combinatorial interpretation of this binomial coefficient that we're looking at? So we could say that this is the number of subsets of size k and 1 up to n minus k plus 1, but we're going to use just a slightly different, essentially the same interpretation, but just a tiny bit different. So remember, this is the number of binary sequences binary sequences of length equal to n minus k plus 1. And so these are sequences of that length, where every entry in the sequence is either a 0 or a 1, and the number of ones is k. Okay, so if you just look at which positions these ones appear in, that's a set of size k in 1 up to n minus k plus 1. So we see that that's the same as this binomial coefficient. Okay, so let's see how that works out in the illustrative case that we're looking at here. We want to look at these, in this case, we're looking at 5 choose 3, that's the number of sequences of length, of length 5 with 3 ones. So we can just write all of those down. It's not very hard. So we get 0, 0, 1, 1, 1. We should write them kind of in dictionary order. That makes it easier to keep everything straight. There's the first 5, and all right, the second 5 over here. So where we got to? We've got 1, then you want 0, 1, 0, 1, and then 1, 0, 1, 1, 0, and 1, 1, 0, 0, 1, 1, 1, 0, 1, 0, 1, 1, 1, 0, 0 is the last one in dictionary order. And so we want to show, so these are our binary sequences, as we mentioned here, and we need to show that they correspond to the gappy sets. But as we said here, subsets correspond to these kind of binary sequences. Gappy sets correspond to binary sequences with gaps in, with no adjacent ones. And so what we can do is, for each of these sets, we can make a gappy sequence of length 7. What we do is we just start copying the sequence here. Let's do this in orange maybe. So we copy the sequence, the 0 and the 0 and then the 1. We don't necessarily need to insert anything to leave this first one on its own, but to make sure that we have gaps for the remaining 2 ones, we need to do some insertion. So we're going to let's see, we're going to insert an extra 1 here, extra 0 here, and then we put this one in, and then we've got this one here. Again, that needs to have a 0 inserted to the left of it. Okay, so now we started with an arbitrary sequence of length 5 with 3 ones, and now we've got a gappy sequence of length 7 with 3 ones. And we can do that to all the rest of these things. Okay, so let's do it to this one here. Okay, so we copy the 0, 1, 0, and then now this next one, we have to pad it with a 0 to the left. And then this last one here, we need to pad that with a 0 to the left as well. Now we've got a gappy sequence of length 7. And we carry on. Let's not do it for all of them, but let's maybe go over and do another couple more examples like this one over here. So we take the 1 and the 0, and then you've got this next one here. We need to pad with a 0 to the left. And then we put the 1 in. And then we've got this next one here. We need to pad that with a 0 to the left. And then put in the 1 and the 0. Okay, and let's just do the last one as well. Okay, so we keep that 1, and then we have to insert a 0 to the left of the next one, and another 0 to the left of the next one, and then we've got the 2 zeros on the end. Okay, so let's just write down what we did. Yeah, so for each such sequence, we insert zeros to the left of each one, except for the first one. We don't need to insert a 0 to the left of the first one, okay, because there's no, I mean, like with this one here, we didn't need to insert a 0 to the left because there's no other ones to the left which could be adjacent to it. Okay, you only have to do that after the first one. Okay. Okay, and so what's the length of this new sequence? Well, we started with a sequence of length n minus k plus 1, okay, like as it's set up here, and now we've inserted some extra stuff. How much extra stuff have we inserted, right? We had k1s to start with, and we're inserting zeros to the left of all of them. That would be add k zeros, but we don't have to insert a 0 for the first one, so it's actually k minus 1 zeros. So we've inserted k minus 1 extra zeros, and then this cancels out to give n. Okay. So this gives a bijection between G and K is this set of gappy sequences that we're interested in, and this construction we've just talked about, it gives us a bijection from the binary sequences of length n minus k plus 1 with k1s to G and K, and so these two sets have the same size, and that's exactly what we needed to prove.